So a section of our homework this week is going to be about biological reactions and how ions participate in biological reactions. I'm going to need you guys to read through carefully the instructions given before this section. All of the answers to the questions are given in there. But I wanted to give you guys a little bit of additional instruction in order to kind of help you interpret what you're reading there. So in biological reactions, we have a little bit of different notation and language that we use. We typically start with something that we call a substrate. This is going to be some kind of biological molecule here. And then that's going to go to our product. And they don't use this language, but I want to introduce the idea between in vitro and an actual biological reaction, which would be called in vivo. So in vitro literally means Latin for in glass. And what happens is that reactions that occur inside of biological systems tend not to be always reproducible on the benchtop in a test tube, for instance. So we might have substrate A, we want to make B. We can't get this done inside of a test tube. That's what this is indicating here. So if we're in a test tube, we're not going to get product B. And the reason for that is we need all of the other things that are around in a biological system to make that work. In particular, we need the magical enzymes that exist inside of living things. And these enzymes are what they call catalysts, and they're going to allow us to go from our substrate A over to B. Now, enzymes will be necessary, but sometimes the enzyme needs a little helper with it. And we call that a cofactor. So sometimes we need the enzyme and all of its cofactors, its little helpers around, in order to get our substrate A to go to B. And it is these cofactors that often contain ionized metals. They also talk a lot about a gradient in the instruction, and I want to give you a sense of what that is. So for instance, they talk about a proton gradient where we have these positive hydrogen atoms, right? And a hydrogen atom only has one proton and one electron. So if I take an electron away from it, then all it is just a free proton. So that's why they call this a proton gradient, and we write it with an H+. And what the gradient is the idea that if I had, say, a pool of water and I add one drop and it's got a bunch of protons in it. Well, at first they're all collected together. And all of these positive charges don't want to be next to each other. Okay, they want to spread throughout the bulk of the pool of water until they're roughly all the same distance apart. So these are moving away from one another. And this difference in concentration where I have a whole bunch of protons concentrated in one area and then less of them over here, this is what's known as a gradient. And the reason that they're moving from a concentrated area to a less concentrated area is because this is being further away from each other is releasing energy. So in having a gradient, we're going to release energy. And this is the way a lot of biological reactions are going to power themselves. Okay, this is almost like the biological equivalent of electricity. We're going to create a gradient and store energy in the form of a gradient, and then we're going to release it in order to do reactions. So in particular, when you are looking at the instructions for this week, I want you to pay attention to this table. because this is going to contain most of your answers for the questions. And it's pretty interesting. I'm not going to go through them all, but we just list different ions and then what function they may have in a biological system. You can see that sodium chloride and potassium are all important for nerve impulses. You're moving around these ions in order to produce the electrical pulses that power our nerves, and also fluid regulation. So you may have heard of things like potassium chloride and sodium chloride being called electrolytes, and that they're important to stay hydrated because they're being used to help regulate your fluids. This is for instance, one of the reasons why sweat is salty, right? In order to help regulate your fluid, your body is releasing some of these electrolytes. And then there's a whole bunch of them here. We already talked a little bit about protons. Copper is important as a cofactor. We talked about how there's charged metals in cofactors. Your bones are made out of calcium. Magnesium is important to plants and to a little bit lesser degree for nerve control. And there's a lot of stuff in here. Carbon dioxide. Our carbonate ions are very important. You get this in the form of carbon dioxide, so you breathe in some carbon dioxide, or your body produces carbon dioxide through respiration, right? And when carbon dioxide goes into water, it forms carbonic acid, which is going to have these carbonate ions. And this can be important. You may have heard of people like hyperventilating, right? Where they start to breathe really fast, and then they get kind of lightheaded and sick feeling and stuff, and then they have them breathe into a paper bag. That's because they're breathing so hard that they're blowing off all of their CO2. They're lowering the amount of carbonate ions in their blood. And then you have them breathe into a paper bag because then they're recycling the carbon dioxide. They're not just blowing it off into the atmosphere. They're breathing the carbon dioxide they just breathed out back in. Okay. And that helps you. In the opposite way, if you were in a submarine at the bottom of the ocean and you're breathing off the carbon dioxide and it can't go anywhere and mix with the atmosphere and you keep breathing it back in, eventually you're going to get to a point where you have so much carbon dioxide in the air that it starts to get kind of toxic to you. And that's where you start to have trouble breathing, is the buildup of CO2 that typically happens before you even run out of oxygen. One thing I do want to elaborate on a little bit now, though, is this PO4, these phosphate ions. So this here is what they call ATP. Adenosine, which is this guy right here, triphosphate. And what this is really your energy currency. So we talked about how we build up gradients. What we're typically trying to do with those gradients is make an ATP, okay? And this is where we're storing our energy that we're going to use for most of our biological reactions. And what winds up happening is you build up this chain of these phosphate groups over here, and you're going to selectively cleave one off, and that's going to release a bunch of energy. And that energy is going to be used to power the reactions. So this is like our little storage bank of power for most chemical reactions. We want to be able to generate this and then get it to wherever we need chemical reactions to happen. Usually you wind up just cleaving off one, but in some circumstances you can actually cleave off a second one as well. And then you're going to have to go back and use the remaining portion. you're going to have to regenerate ATP in what they call the Krebs cycle, or the citrus acid cycle, in order to get back to this guy where you can use it again. So your body never waste stuff. It's not just going to get rid of this in the end. It's going to take this guy and it's going to regenerate it back. I also want to note really quickly just a little something about how this is all drawn out here. This is something you're going to need to become familiar with if you want to continue on into organic chemistry. Each one of these lines is indicating a chemical bond. Each one of the atoms is indicated by a letter that we're familiar with as it's being its elemental symbol. Okay. You'll note that there are different kinds of bonds. Like, for instance, this one is a double bond written by two lines here. This one is what they call a wedged bond. It's indicating that it's coming out of the page at you. It's trying to give it some three-dimensional perspective. And you'll notice that there are little sections where two bonds meet that do not have a letter on them. All right, it doesn't indicate that there's any element here. And that's because chemists are really lazy when we write things. So everywhere where you don't see anything, that's actually where there's a carbon. Okay. And not only is there a carbon there, that carbon is always going to make 4 bonds, because that's what carbon does. It makes 4 bonds. We're going to assume that, for instance, here where it's bounded here and it's bound here, there's even 2 hydrogens bound to this carbon that we're not drawing. So we're going to fill in the hydrogens wherever necessary to make sure that all of our carbons have hydrogens. And that's because most all organic molecules, or biological molecules for that matter, are majority made out of carbon, and they're typically terminated with hydrogens wherever there isn't one of some other carbon or some other heteroatom. That's what they call these guys here that we're indicating. And we're just not going to draw them all out.